is a binary signal, and it is represented by plus v or minus v. Now in channel there will be presence of noise, and it will be mixed with or added with the transmitter signal, that is plus v or minus v. So received signal after addition from the noise, it will differ from plus minus v. So here we are assuming that noise is Gaussian noise with zero mean. So noise will be our consideration will be Gaussian noise with zero mean. Now let's take a case. Here you can see our transmitted voltage was V, and a noise is mixed, and T is the beat duration. T is our beat duration. It started from T1 and ended at T2. Now due to the mixture of noise, the waveform will differ from original transmitted waveform, and it will be maybe something like this. A dip occurs maybe at t is equal to t1 plus del t. Now see, at the receiver side, we'll take sample of the received value. We can take sample here, we can take sample here, or we can take sample here also. So at any point we can take sample, and after sampling we'll decide whether plus v or minus v was transmitted, and based on this we'll determine transmitted signal is binary 1 or binary 0. So in this case, if I sample at t is equal to t, the t time, t is equal to t1 plus del t. If I take sample at t is equal to t1 plus delta t, the sample value will be negative. The sample value will be negative. As a result, error will occur, and that should be avoided. Now to reduce the error, to reduce this kind of error, sampling error, and determine the actual sampling time, we use filters. We use filters in communication system. To reduce so main purpose of the filters is to reduce the errors in communication system and sampling error. Here I have drawn a circuit. In this case, the input is the original message signal or original transmitted, maybe xt, and it is added with noise nt. xt can be either plus v or minus v. So this mixer of these two signals will be passed through an integrator. So this part of the circuit is the integrator. So that is our integrator, and that part is an high gain amplifier. Now this integrator have two switches. That is switch 1. Purpose of this switch is to reset the capacitor after each beat interval. So that switch will discharge the capacitor after the beat interval. So maybe at beginning of t1, at the beginning of t1, this will close, and it will discharge the capacitor completely, so that the new integration don't have any influence from the past integration. And after this integration over the beat interval, that is time t, another switch, that is SW2, which will sample. Now this output is yt. This SW2 takes sample of the yt at time t is equal to t. So this SW2 will close at t is equal to t is equal to 2t, t is equal to, so this SW2 will close t is equal to t, 2t, 3t, like this. So it will close after integer number of time period t, and this sample signal is represented by y capital T. This SW1 this switch is known as dump switch because it will dump the capacitor after each bit interval. SW2 is known as sampling switch. Now we need to calculate the signal to noise ratio at the output of the this filter. This filter is known as, this kind of filter is known as integrate and dump filter. This filter is known as integrate and dump filter. Now we need to calculate this signal to noise ratio for this integrate and dump filter. So objective determine SNR of integrate and dump filter. So output yt can be represented by integration of 0 to t, because it is integrating over the bit interval 0 to t, and it is integrating this addition xt plus nt, and there will be a slope that is 1 by rc, and this rc will consider it as a tau, or you can write it is equal to yt is equal to, note here we are using y capital T, not y small t. Y capital T represent the sample value after closing the switch. So these are the sample values, and these are the intermediate values. So yt is 1 by tau 0 to t xt dt plus 1 by tau 0 to t nt dt equals, so we'll consider it as xot plus not. We'll determine individual components separately. So let's find out what will be the xot. So xt can be either plus v or minus v. Let's consider xt is plus v. Xt is a pulse of v and time t. So integration x0t will be 1 by tau Remember, our objective is to determine the signal to noise ratio. So signal to noise ratio is the signal power by noise power. So once I get the signal values at the output side, x capital T, this should be capital T. So once I get the output sample value for the signal component, we can square it up and we can get the signal power. So signal power will be so here I am considering we are taking power with respect to 1 ohm resistance. So that is V square by R. R is 1 ohm. So it is signal power is normalized with respect to 1 ohm resistance. So x0 T square, that is V voltage square by resistance, and it will be V square T square by tau square. So that is the signal power. Next we need to find out the noise power. Now we need to determine the noise power. Now noise is a random process, and each random process have some power spectral density, and from the power spectral density we can determine the power. So in general we can write that the power is computed by integrating the power spectral density from minus infinite to plus infinite. Similarly, for our noise power, the mean square noise power can be determined as, so our original sample value of the noise was n0t, so we'll take the square and take the average. So that is the mean square value of the noise. It will be minus infinite to plus infinite. Power spectral density, output power spectral density. So that we need to determine for the noise power section, similar to this expression for our noise. We need to determine this expression. Here n0t was the sample value of the noise, and n0 square t is this mean square value of the noise, mean square noise power. And SNO is the power spectral density at output, at filter output. Now at the input side of the filter we have some noise, and output side of the filter we have a filtered version of noise. Now these two power spectral density at the input of the integrator and power spectral density of the at the output of the integrator is different, and that can be seen as, maybe that is the input side power spectral density of the filter, and you have filter with transfer function HF. You have power spectral density at the input side, noise power spectral density. If we pass it through a filter with transfer function HF, output will be SNOF. Now these two things are related by SNO, output power spectral density, and input power spectral density. These two are related by SNOF equals absolute square of the absolute value of the filter transfer function into SNIF. So you can see we need to determine these two things, these two expressions, before determining the noise power. Now, before beginning of this filter calculation, we already told you that we are assuming white Gaussian noise. We are assuming the Gaussian noise, and here we will assume the noise is white. Gaussian noise with zero mean. And power spectral density of white noise, so noise originally a Gaussian noise, and its power spectral density will look like this. So it will be uniform. So that axis, y axis is SNIF, and x axis is F, and the power spectral density is white. So each and every frequency component have same strength, and the height is n0 by 2. So this height is n0 by 2. So for white Gaussian noise, SNIF equals n0 by 2 for all frequencies. So it is constant for all frequencies, and value is n0 by 2, where n0 is noise variance. N0 is noise variance. Next, we will determine the filter transfer function, absolute value of the filter transfer function. So we'll determine this term, absolute square of the absolute value of the filter transfer function. Now we know that we are using integrator. So integrator transfer function basically HF is equals 1 by j omega c, j omega rc equals 1 by j omega tau. So that was our original integrator transfer function. Now see, in our situation, the integrator starts at t equals 0. It starts at t equals 0 and stops at t equals t. So integration time period is 0 to t. So that's why this integrator integrates, this integrator transfer function is for that integrator which integrates from 0 to infinite. So that is applicable for 0 to infinite. Now we are we start at t is equals 0 and end at t equal t. So the integrator transfer function in our case will be hf equals 1 minus e to the power minus j omega t by j omega tau. You see, we need to determine absolute value. So we'll separate the real part and imaginary part. So hf will be 1 minus, so e to the power j theta is cos theta, that is cos omega t, minus j sin omega t. So if I separate the real part and imaginary part, it will be sin omega t minus j 1 minus. Now absolute value, so if I multiply both sides, now absolute value of hf square equals sin square omega t plus 1 minus cos omega t square divided by omega tau square equals, if I simplify this, it will become 4 sin square omega t by 2 by omega tau square. So if I write omega equals 2 pi f, it will become sin square pi f t by pi f tau square. So h f square equals